Hello to you all and welcome to my presentation. My name is Owen and unfortunately today I cannot be with you in person. The work to be presented was done as part of a collaboration between the University of Malta and the Malta Air Traffic Services. Let me first provide an overview of the presentation. Initially, I will give a brief introduction followed by the background theory related to the design of a lumped component unequal Wilkinson power splitter. Then the design details will be given together with the simulation and measured characterization. Finally, some concluding remarks will be made and possible future work will be highlighted. Couplers and power splitters feature in various microwave and RF applications. These devices are typically based on quarter wavelength transmission line structures, including microstrips or strip lines, which are designed at a particular resonant frequency. Implementing these devices for high-power VHF applications is typically prohibited due to the large wavelength, cost considerations, and power handling. This work revisits and derives the complete set of design equations for a lumped component two-way unequal Wilkinson's power splitter by using standard circuit theory rather than odd and even mode analysis. The use of standard circuit theory offers a simpler yet effective analytical design methodology. Even and odd mode analysis relies on having symmetrical networks. If the circuit is non-symmetric, applying even and odd mode techniques is no longer straightforward. Without symmetry, the advantages of even and odd mode decomposition are lost, and standard circuit theory becomes more appropriate without requiring special transformations. Using the derived equations, the design of a three-way lumped or discrete component unequal high-power splitter for the International Aeronautical Emergency Frequency is presented. The design is based on modular two-way Wilkinson's power splitters. Although N-way power splitters have been reported in literature, the proposed two-stage modular solution facilitates the optimization and testing of the lumped component implementation by independently designing the different component values of each stage. The aircraft emergency frequency is reserved and used on the airband for emergency communications for aircraft in distress. Civilian flight operations use a VHF frequency of 1 to 1.5 MHz, which is also known as the International Air Distress or VHF Guard. The flight information region managed by the Malta Air Traffic Services covers a stretch of the Mediterranean Sea from Tunisia to Greece, without any land-based radars for most of the way. Thus, to optimize the 1 to 1.5 MHz transmitted signal power in various directions, a three-way unequal power splitter is designed to deliver 70% of the power towards the eastern sector, 20% towards the western sector, and 10% towards the southern sector. This slide shows the FIR managed by the Malta Air Traffic Services. Here we show the schematic diagram of an unequal Wilkinson's power splitter, which consists of four quarter wavelength transmission lines with characteristic impedances Z01, Z02, Z03, and Z04, and an isolation resistor Ri. Transmission lines 1 and 2 are used to split the power fed at port 1, while transmission lines 3 and 4 act as an impedance transformer to achieve an adequate match at ports 2 and 3. Ports 1, 2, and 3 are terminated in a characteristic impedance of Z0. The power in the lower path PIL is K squared times the power in the upper path PIU, where K is a fraction between 0 and 1. Thus, ZIU is K squared times ZIL, where ZIU is the input impedance seen from the upper path at port 1, and ZIL is the input impedance seen from the lower path at port 1. Given that the input impedance seen at port 1 is equivalent to the parallel combination of ZIU and ZIL, and which must be equal to Z0 for matching purposes, one obtains these two equations. In this type of splitter, when the power is fed in port 1, voltages at node 2 and node 3 will be the same, such that P3 is K squared times P2, where R2 and R3 are the equivalent loads seen at nodes 2 and 3 respectively. Thus, expressing this as follows gives the values of R2 is equal to K Z0 and R3 equal to Z0 on K. Since the transmission lines have a length of a quarter wave, the respective characteristic impedance of each section will be given by the highlighted equations by calculating the geometric mean of the input and output impedance of each transmission line section. Existing literature doesn't provide a proof for the value of the isolation resistor Ri. If power is fed into port 2 while port 1 and port 3 are terminated with a load resistor of Z node, node 3 would be at a virtual ground due to the high isolation provided by Ri, and so V3 would be equal to 0. Thus, the transmission line sections 2 and 4 would be out of circuit since no power would be flowing through them. The impedance seen at node 2 would be equal to the equation marked on this slide. By making Ri the subject of the formula and using the equation marked in red for R2, one obtains an equation for the isolation resistor Ri. The equation for Ri can also be obtained by considering that the power is fed into port 3 and terminating ports 1 and 2 with a load of Z0. In this case, node 2 would be at virtual ground due to the high isolation provided by resistor Ri, and so V2 would be equal to 0. Thus, the transmission line sections 1 and 3 would be out of circuit since no power would be flowing through them. The impedance seen at node 3 would be equal to the highlighted equation. By making Ri the subject of the formula and using the equation marked in red for R3, one obtains an equation for the isolation resistor Ri. This equation can also be expressed as the sum of R2 and R3. The proposed design is based on the lumped component equivalent circuit of a quarter wave transmission line. Consider a short lossless transmission line section with length L and characteristic impedance ZOX. Its transmission parameter representation based on the telegrapher's equations is highlighted here, where beta is the transmission line phase coefficient, VA is the sending end voltage, IA is the sending end current, VB is the receiving end voltage, and IB is the receiving end current. If the transmission line length L is equal to a quarter wave, then this equation simplifies to the indicated equation. The lossless transmission line section can be transformed to a lumped component by equivalent circuit at a resonant frequency f. Obtaining the admittance parameters YAB and YAA for the circuit shown on this slide and relating them to the same parameters from the previous equations, one obtains the expressions highlighted in blue. Thus, inductance L and capacitance C can be related to the characteristic impedance of the transmission line section by these equations. Although N-way power splitters have been proposed in the literature, in this work, an alternative 1 kilowatt modular two-stage power splitter is proposed. The proposed solution facilitates the optimization and testing of the lumped component implementation by independently designing the component values of each stage and limiting as much as possible their associated parasitic components. While SMA connectors were used for prototyping purposes, these were eventually changed to N-type connectors in the final version. Since the power fed into the input port needs to be split into the three respective outputs with a zero point 0.7 to zero point 0.2 to zero point 0.1 ratio, K needs to be equal to 0.655 for the first stage and K must be equal to 0.707 for the second stage. The required characteristic impedance of the transmission line sections of each stage was determined, and then the equivalent inductance L and capacitance C of each transmission line section were found at a frequency of 1 to 1.5 MHz. The characteristic impedance of each transmission line section and the isolation resistor value for each stage are presented in the shown table. This slide shows the scattering parameter simulation results of the designed power splitter. Each port exhibits a low voltage standing wave ratio, with minima near a frequency of around 1 to 1.5 MHz, guaranteeing a good matching condition at those ports, particularly around the design frequency. This is also confirmed by the plot of the return loss. The insertion gain plots indicate the intended unequal power split. The frequency response of the power division ratio is relatively flat across the simulated band. Scattering parameters S12, S13, and S23 show the high interport isolation achieved by the design. High isolation is important so that signals on one port do not couple significantly with the others. In the actual implementation, the inductors were designed as high-quality factor air-cored coils using a copper wire of gauge AWG14 on a 9.5 mm format to be able to handle the 1 kW input power. Each inductor was manually designed and characterized via a one-port measurement carried out using the Sigland SVA 1032X vector network analyzer to guarantee that the required inductance was achieved. The capacitors were implemented as multi-layer high-voltage ceramic capacitors with a voltage rating of 500 volts. High-frequency thin-film high-power chip resistors were employed for RI of both stages. Thin-film chip resistors were used because they feature low parasitic effects, particularly low unwanted inductance and capacitance, thus limiting performance degradation above tens of or hundreds of megahertz. The thin film deposition process also allows for very stable, precise resistance values with excellent temperature coefficients. This precision helps maintain consistent performance over a wide range of frequencies and high power operating conditions. The values of the capacitors were optimized to compensate for any parasitic capacitance arising from the inductors while making sure that standard capacitor values were used. The table shown on this slide represents the values of the components used in the actual implementation. The design was implemented on a high-performance FR4 double-sided printed circuit board with a high glass transition temperature, low coefficient of temperature expansion substrate, featuring a relative permittivity of 4.58 and a tangent loss of around 0.02. The ground plane areas underneath the designed inductors were edged away to limit any coupling effects. The measured performance of the implemented power splitter was obtained using the Sigland SVA 1032X VNA. The test setups used for the characterization of the power splitter are shown on the slide. Since the VNA has only two ports, the measurements had to be split into three categories: VSWR and return loss port measurements, insertion gain measurements, and isolation measurements. Before the measurements were carried out, a two-port through reflection line calibration over the frequency range of interest was carried out. This ensured that the reference planes for the measurements were taken at the end of the test cables, and that the cable and the connector effects were removed. This slide presents the measured performance of the designed unequal power divider. Using the insertion gain plots, one can notice that the obtained power division ratios are 71% on port 1, 19.8% on port 2, and 9.2% on port 3, respectively. These values are close to the desired specifications. A return loss of less than -28 dBs was obtained on each port at a frequency of 1 to 1.5 MHz, while a good isolation of around -60 dBs from port 1 to ports 2 and 3 and an isolation of -27 dBs between ports 2 and 3 were measured. The differences noted from the simulation results can be attributed to any uncompensated parasitics of the passive components and to the actual values of the isolation resistors employed in the design, which were slightly different from those given by the derived equations. The simulation results presented in the previous slides were obtained with ideal passive components, and thus the simulated power splitter features a sharp and narrow band response around 1 to 1.5 MHz. The finite quality factor of the reactive components and their parasitic components explain the variation in the results obtained for the actual implementation. Nonetheless, the performance attained is adequate for the given application, even though further optimization is required to improve the isolation between ports 2 and 3, which is related to the proximity of the networks connected to these ports. This work presented an alternative derivation of the complete set of design equations for a two-way lumped component Wilkinson's unequal power splitter by using standard circuit theory, rather than odd and even mode analysis. The use of standard circuit theory offers a simpler yet effective analytical design methodology. Based on these equations, the design of a three-way lumped component unequal high power splitter for the 1 to 1.5 MHz aircraft emergency frequency was presented, while using a lumped component equivalent circuit of a quarter wavelength transmission line. The proposed solution alleviates the difficulties of implementing high-power VHF applications as a microstrip or stripline structure. A measured return loss of less than -28 dBs was obtained on each port at a frequency of 1 to 1.5 MHz, together with an isolation of around -60 dBs from the main output port to the other output ports. The following are some research directions that could extend or build upon the work presented in this paper. One may examine whether the proposed approach can be generalized to power splitters operating at several discrete frequencies within the airband. One may also explore the applicability of the derived design equations to broadband or multiband Wilkinson splitters. This may involve modifying the lambda element quarter wavelength equivalent circuit to maintain low return loss and high isolation over a wide frequency range. Since the design targets high power operation at VHF, a thorough evaluation of the thermal behavior and dissipation, especially in the resistors and inductors, would be beneficial to ensure long-term reliability. Long-term reliability studies can be conducted to determine how performance metrics, including return loss, isolation, and insertion loss, degrade over time under continuous high-power operation and varying environmental conditions. While thanking you for your attention, I would like to invite you to contact me via my email address in case you wish to discuss any part of this work.